Okay, sorry for the little glitch. It's a little hard to coordinate the screenshot here and get the animation to work with the software I'm using, but I think I can get it to work this time. I think I've got it lined up. Here we go. So if you look at these on the first one, t, and if you can see the bar, it's running from 0 to 2 pi. During that time period, this blue dot goes around the circle exactly once, but during that same time period, this guy's flying twice as fast, so he maps out 2 copies of the circle when this guy maps out 1 copy of the circle. Both running from 0 to 2 pi, but this one going twice as fast. So again, you can get the same curve with different parametric functions, but if you think of it as a path, the way it maps out the path is a little bit different on these two examples. Okay. So again, you can think of it as being a path mapped out, not just the graph itself. Okay. Here was another example in the notes. Sketch the parametric curve for x equals cosine t and y equals cosine squared t. Well, if you look at that, y equals x squared if x is cosine. So you get the parabola y equals x squared, except x and y, both depending on cosine, are trapped between -1 and 1, and the y value actually is between 0 and 1 since it can never be negative. Let's see if I can get that to animate. Let me move it over a little bit and maximize. There you can see as we go between 0 and 2 pi, this thing would just oscillate forever between -1 and 1. Okay, now I'm going to show you how to get either a calculator or other software to graph a parametric function. It's a pretty simple idea. You just take t values and you'd make a column for x, a column for y, and plot points. But when the graphs become more and more complex, which actually give you the really neat graphs to look at, it would take forever if you had to do this by hand, but software can do it very, very quickly. So let's start with the graphing calculator. Okay, so if you'll bear with me a little bit, I have an emulator version of the calculator here. And I'll try to show you how we're going to do this. We're going to plot this function. So if you hit the mode button, on the 4th line down, right now I have function highlighted, so that when I hit y equals, I get regular functions, and when I hit the button right here, I get x values for it. But if I go down and I change that over, we can set it to parametric functions, the second entry. And now this button will be t values. This corresponds to the 4 different menus here. When we do functions, parametric, polar, and sequences, we have a different variable, x, t, theta, and n. When we do parametric, this button will give us our t we want. And now when you hit y equals, for function number 1, number 2, number 3, instead of just having y, you have x and y. So, well, let's see. I don't even have this one set up yet as a parametric function, but what I can do, one reason I have this example is to show you, if I was going to plot this thing as a Cartesian function, we would have to solve for y. I don't have to do that here. I can just let y be t. So let's go down and let y be t. And then x would be, y to the 4th would be t to the 4th. So t to the power, let's move it up a little, 4. Then we're going to do minus 3y squared. Minus 3, well, y is t squared. So if you have a function that's solved for x or solved for y, it's really easy to write the parametric function. Just let the variable being used be t, in this case y, and then the one that's solved for, instead of y to the 4th minus 3y squared, we can plug the t in for y. Okay, now the window we use is very, very important when we plot a parametric function. Remember, you have to tell it what t values to use. Just like if you were doing it by hand, you would make a table. Well, in the calculator, that's got to be pretty explicit here. I'm going to hit the window button, and we're going to tell it what t's to use. If this involved trigonometry, I would do 0 to 2 pi, which is what we see here, and you want a small step size, about 0.1, so that you get enough points to see what's going on. This one, however, does not involve trig, so I want to make sure I include some positives and negatives. I'm going to go from -10 to 10. So I'll do -10 for my smallest t value that I use, up to 10, and I'm going to use a step size of about 0.1. That way it'll go -10, -9.9, -9.8, and count by 1/10 and get lots and lots of points. And then you can set the x and y axis exactly as you would before. Okay, so the new addition is we have to tell it what t's to use. You have to explicitly tell it, I want to go from this t value to this t value, and what you want the increments to be. Once you have that set, you can hit the graph button and it'll map this thing out. Okay? So we get basically a fourth degree polynomial, but it's x solved for y, so it's on its side here. We have a y to the fourth polynomial. It has this sort of W shape but turned sideways. So as long as you're in parametric mode, when you hit y equals, you can enter your functions of t for x and y. And if you have something like this, x equal a function of y, just let y be t, and then transform x into this function of t. If I had y equals, I could do the same thing. Like, let's say we wanted to plot something simple like y equals x squared. Well, if you want to do y equals x squared, just let x be t and y be t squared. Graph, and we'll get our familiar parabola that we know. Okay, so let's move the calculator over and see what I've got for us next in the notes. Okay, another example, I'll show you again how to use the calculator to graph, but I'm going to show you it's also very easy with parametric functions to graph an inverse. Much easier than it is with Cartesian functions because you would actually have to find the inverse. You actually don't have to do that for parametric. So let's start by plotting this function, the square root of t cubed plus 1. So I'm going to hit y equals, and let's just let x be t and then y be our function here. So the square root of t, scoot up a little bit, t cubed plus 1, close the square root. So there we have x equals t, and then our function, the square root of t cubed plus 1. We can graph that. And we get this sort of weird cubic function with a little bump in it here. If we wanted to plot its inverse in Cartesian coordinates, we'd have to solve for t, but we don't have to do that here because we have formulas for x and y. Remember that an inverse is just swapping the role of x and y, so I can do that. The formula we had for y, I'm going to put in to the x value on my second function. And what we had for x, I'm going to put for y. Graph that. And we get the reflection across the line y equals x. Of course, on the calculator, the window is rectangular. If I hit zoom square, it'll take care of that and adjust the window. So there's our function. And it's calculating all these points. There's its inverse, the reflection across the line y equals x. If I wanted to, I could actually put that into the third function. Let's let x be t and then y be t for y equals x. There's the line we're reflecting across to get the inverse. So, point is, on this example, if I can plot something with its parametric equation and I want its inverse, I don't have to solve like we did with Cartesian coordinates. I can just swap x and y because I have formulas for those. Okay, back to the notes. What's left? I just have an example. Here's a very famous example. Let me see if I can get it to line up and animate it. This is called the cycloid, a little complex on its equation. But it's the path. If you put a pin on a wheel and were to roll it and be able to map it out, it's the path that it maps out. So just kind of an interesting parametric function that's been studied in mathematics. And then what else? The last thing. So mainly I want you to be able to graph these things with the help of a calculator or software. And then I showed you when I did an example how easy it is if you have y equals f of x or even x solved as a function of y to just let one of the variables be t and come up with the parametric equations. Going in the other direction is not quite as easy. Sometimes it's a little tricky to figure out how to eliminate t and transform it into a function involving x and y, but that's what I'm going to show you some examples of here on this example 7. So it says eliminate the parameter to write with Cartesian equation.